Hi, I'm recording this video to explain you a small concept in linear algebra. The prerequisites for understanding the proof of this theorem are as follows. Number one, what is the meaning of a system of linear equations? Number two, what does it mean to solve a system of linear equations? Number three, what do you mean by a vector space over R? Number 4, what do you mean by linear combinations? Number 5, what do you mean by linear independence and linear dependence? What does it mean to say that a set generates a vector space? That's how you write the statement as. This simply means that S generates V. And what do you mean by basis of a vector space? And what is the meaning of dimension of a vector space? So I assume that you might have gone through all these concepts before you start this video, or if not, you pause this video and have a look at all these concepts and come back. Okay, so what's the theorem statement? It says that if you have a vector space of dimension n, let us say that m is any number greater than n, any natural number greater than n, then any set of m vectors, of course from the space V, is linearly dependent. So recall what linear dependence means. It means that in a scalar, in a linear combination of these vectors equating to 0, you will have at least one scalar which is non-zero. Okay, so let's look at this theorem with the help of an example. Let us say we have the vector space R2. We know that its dimension is equal to 2 because R2, which is the xy plane, is spanned by two vectors 1 0 and 0 1. So you have a basis consisting of these two vectors 1 0 and 0 1, which has only two vectors, and hence the dimension of the space is 2, and that's what the definition of a dimension is. But what happens if you take three vectors in this set? Let's for simplicity keep the two vectors as 1 0 and 0 1, and let's take the third vector as any other vector. Say for example, let's take 1 comma 2. So this is 1 comma 2. So if I take 1 comma 2, then clearly this set is linearly dependent, because 1 comma 2, oh, this looks like 2 comma 1. Okay, anyways, if you write this as 2 comma 1, then the vector 2 comma 1 can be written as linear combination of these two vectors. There is 2 times the first vector plus 1 time the second vector. So of course this set is linearly dependent. Not only this set, you take any set containing 4 vectors, 5 vectors, or any set containing more than 2 vectors, it will always be linearly dependent, and that is what we are going to prove in this theorem, the proof of this theorem. Okay, so let us begin the proof. Step 1. We know that the dimension of the vector space is n, which means that there exists a basis of V such that the number of elements in the basis is n. Let us say that those n vectors are, say, v1, v2 and so on up to vn. And since it's a basis, we know that L of B will be equal to V, which means that B generates the vector space V, which means that every vector in V can be written as a linear combination of the vectors in B. Okay, let's give them equation numbers. So you have 1 and 2. Okay, now let's talk about any set that contains more than n vectors. So let S be any set containing m vectors of the vector space V. Let us denote the vectors in S as W1, W2 and so on up to Wm. Okay, so we see that the cardinality, the number of elements of S is equal to m. Let's call this as 3. Let's call this as 4. Our aim is to show that the set S is linearly dependent. So how do you show that any set is linearly dependent? You show that you start with a linear combination of the vectors in S, which is equal to the 0 vector, and you prove that there is at least one scalar in that linear combination which is not equal to 0. So let us start with any linear combination. There are m vectors, right? So we'll need m scalars. So let x1, x2 and so on up to xm be real numbers such that x1 times the first vector of S plus x2 times the second vector of S plus xm times the mth vector of S is equal to the 0 vector. What was the last equation number? It was 4. So let's call this as 5. What is our aim? Our aim is to show that at least one among these xi's are not equal to 0. Yeah, for I between 1 and m. This is our aim, to show that at least one scalar, it can be x1 not equal to 0, or it can be x2 not equal to 0, or xm not equal to 0. Our aim is to show that at least one scalar is not equal to 0. How do we show that? Let us use what we have with us. We have a very important data that L of B is equal to V, which means that V is generated by the basis B, which I had said, the meaning of which is every vector of V can be written as a linear combination of vectors in B. Okay, so we have a few vectors here, W1 up to Wm. So all these Wi's, they belong to the vector space. W1, W2 and so on up to Wm, they all belong to the vector space V, which is equal to L of B. Now what will W1 belonging to L of B mean? It would mean that W1 can be written as a linear combination of vector V1 up to, we'll need n scalars, up to the vector Vn. What would W2 belonging to L of B mean? It will mean that W2 can be written as again a linear combination of V1 up to Vn and so on. We have Wm belonging to L of B. The same thing happens to Wm. It can be written as a linear combination of V1 up to Vn. Okay, but we have created a problem over here. All the wi's, they look alike because the scalars that we used are the same. So let's give them different scalars. So if we see a matrix kind of arrangement over here, so we will need at least two subscripts to define to denote the scalars. So let's call these scalars a1 up to an by giving one more number, which is, say, the number 1. So it will be a11 and this will be an1, and here the next one would be a21, a31, and so on up to the last one is an1. Okay, for this, for w2 you'll have a12 and so on up to an2. Here it will be a1m, so on up to a&m. Let's call this system as, say, system star. Okay, so we have written each wi as a linear combination of vectors v1 up to vn, but we already had a linear combination of w1 up to wm. Now things are going to get a little bit more complicated before we solve it. So we will use equation number 5 and we will substitute each wi in this equation number 5. So what will we have? So it was, let's say, what was 5? It was x1 into w1. I'll just show you again. So x1 into w1, but what was w1? W1 is this thing. Okay, so it can be written as a1 something v1 plus so on up to a1 something, no, it was an something vn, plus the next one was x2, it was a2 something, no, it was again a1 something v1 plus so on up to an something vn, plus the last one was xm into a, again it was a1 something v1 plus so on up to an something vn, and we had given more subscripts. We call this as 1, we call this as 1, we call this as 2, 2, we had called this as m, and we had called this as m, and we had said that it's equal to the 0 vector. So at the end we have a linear combination of only vi's, and we are saying that this linear combination is equal to 0. So this tempts us to take the coefficients of v1 common. So okay, so what do we have here? We have something into v1 plus something into v2 plus so on up to something into v, there were n vectors equal to the 0 vector. Let's look at the first something. It was a11 into x1 plus a12 into x2 plus a1m into xm. So let's write it. It was a11 into x1 plus a12 into x2 plus so on up to a1m into xm. Let's look at the coefficients of v2. Okay, there are no coefficients of v2 we have written, but yes, we can make a guess. The coefficients of v2 would be this x1 multiplied by a21 right? So it will be a21 x1 plus a22 x2 plus so on up to a, what would be the next? The last one would have been a2m, yeah, a2m xm. And let's look at the coefficients of Vn now. The coefficients of Vn are x1 into an1 plus x2 into an2 plus xm into anm. So you have an1 x1 plus an2 x2 plus so on up to anm xm. So you have a linear combination. Recall that these are all scalars. The ones that I have put in red, they are all scalars. If you call the first scalars as alpha 1, so you have something like alpha 1 into v1 plus alpha 2 into v2 plus so on into alpha n into vn is equal to the 0 vector. Let me switch back to my original color. So it is alpha 1 v1 plus alpha 2 v2 plus so on up to alpha n vn is equal to 0. But what is this? You're saying that the linear combination of the vectors from the basis is equal to 0 vector, and you know that basis vectors, they form a linearly independent set, which means that all these scalars alpha 1, alpha 2 and so on up to alpha n have to be zeros. But what were the original values of alpha 1? Alpha 1 was the first coefficient, alpha 2 was the second coefficient, and alpha n the last coefficient. Okay, so let's make that statement. Since B is a basis, therefore B is linearly independent. Therefore, the first coefficient, what is the first coefficient? a11 x1 plus a12 x2 plus so on up to a1, what was it, m xm. We are saying that the first scalar is 0. Also the second scalar is 0. What was the second scalar? a21, then it was all 2 2, and then it goes from 1 2 up to m, and the last one was a n1, it was all n, and it goes up to, from 1 it goes to 2 and up to m. Okay, so this is the second scalar, second scalar. This is the nth scalar, x2 plus so on up to xm is equal to 0, and here you have into x1 into a plus an2 into x2 plus so on up to anm xm is equal to 0. What do we have here? We have a system of linear equations in how many unknowns? I'll have to use another color again. You have m unknowns, and how many equations do you have? You have n equations. This is what tells us that there are n equations, and this is what tells us there are m unknowns. So you have n equations and m unknowns, but we see that this m is greater than n, which means that number of unknowns, right? Number of unknowns is greater than the number of equations. What does this mean? Recall our lemma. I'll go back. Oh, I forgot to give you the lemma. Okay. There is a proposition which says that if you have a homogeneous system, if a homogeneous linear system has more unknowns than equations, then the system has a non-trivial solution. Non-trivial means non-zero. Now what does this mean? This means that you have a solution. Say for example, let's take 2x plus y is equal to 0. This is a system of only one equation in two unknowns. So of course the number of unknowns is greater than the number of equations. What is the solution of the system? Solution set. The solution set S is actually the collection of all xy, of course belonging to R2, that satisfies the equation. Now what is this? Which is a line. Which is a line. This is a solution set, and as we see that the solution set is a line, it will contain infinitely many points. And of course, if it has infinitely many points, it is not difficult for us to find out a non-zero solution. So we can take a non-zero solution as, say, if I put x is equal to 1, I will get my y as minus 2. So 1 comma minus 2 is a solution, and we have infinitely many other solutions, but we are interested in only non-trivial solutions. Okay, let's come back to our proof. We stopped over here. We have more unknowns than equations. This means that the system, what was the system of equations here? The system of equations is this that you see. Let's give it double star. So we can now say that the system double star has a non-trivial solution. This means that there exists at least one xi not equal to 0 such that x1, x2, so on up to x. I think we had m scalars, yeah, satisfy the double star. We are not interested in this. In fact, we are only interested in this. We got our xi not equal to 0, and hence proved, right? This is what we were looking for. We wanted to show that at least one of the x's is not equal to 0, and we have done that with the help of this very important theorem, a lemma. That's it. See you later.